Hi everyone. Today I'm going to introduce my final year project, Deep CNN LSTM Supervised Model and CNN Self-supervised Model for Human Activity Recognition. Human activity recognition has gained significant interest from researchers in the past decades. With the quick development of wearable sensors technology and the high availability of smart devices. In this paper, we propose a CNN-LSTM attention supervised framework for HAR data classification, which automatically extracts spatial and temporal features from the smart device sensory data. However, a large amount of labeled data is typically required to perform supervised learning, which can be lacking due to data privacy concerns and the high cost of manual labeling in the real-world scenarios. Therefore, learning from the large amounts of unlabeled data become crucial. To this end, we proposed a self-supervised learning framework that learns useful representations from unlabeled sensory data. The experiment result demonstrates the TSSL robustness with data imbalanced issue. With only 5% labeled data fine-tuning, TSSL approach significantly improved the model performance compared to supervised training, who is training with full labeled data. Last but not least, from the hardware sensory perspective, we proved that the smartphone accelerometer can produce more accurate classifications. In this paper, we test the model performance on 3 public datasets, UCI-HAR, HSAR, and HAPT. The first 2 datasets are well balanced, ready for experiments, and we prove the effectiveness of different sensors with HHAR datasets. While 6 imbalanced classes in HAPT datasets from the data point count bar chart. We try to oversample those classes by replication techniques to make sure the sufficient performance. Most importantly, we can test the model robustness in these datasets. Here is the architecture of supervised learning. First, the HAR datasets will be pre-processed and passed to the supervised learning model. There are 2 conventional layers by 1 LSTM layer, 1 attention layers, and a classifier. In this paper, we aim to investigate the attention layer effect. Hence, we compare the performance between CNN-LSTM model and CNN-LSTM attention model. Here is the one-dimensional CNN self-supervised model with 2 stages. Stage 1, self-supervised pre-training, where we propose 4 pretest task transformations to help the model learn feature representation from all the unlabeled data. After that, the transformed data is passed to 3 continuous CNN layers, followed by a classifier, and generate the pseudo-labels. We also compute the consistency rules between the original features and transformed features to improve model robustness. After training, the weight of the model is transferred to stage 2. In the stage 2, we will fine-tune the pre-trained model with few true labeled samples. The cross-entropy rules is computed here. Here comes to the experiment results. In Table 1, the CNN-LSTM model performed the higher F1 scores on 3 datasets. Our model also achieved the comparable performance with the baseline result. The result shows that the attention layer did not improve the performance. This is because the time series data already has a natural order and structure that can be captured by the LSTM layer in the model. Hence, in this paper, we suggest using the CNN-LSTM network in a supervised approach. In Table 2, with 5% labeled data fine-tuning, the SSL model achieved higher F1 scores than the supervised learning, which is training with 100% label data. These results demonstrated that in real-world data shortage scenario, SSL is able to learn the data representation from the data itself instead of the labels. Here, we focus on the imbalanced classes in the HAPT dataset. We investigated the SSL effectiveness in dealing with imbalanced class data. We compared the SSL with raw datasets, SSL with oversampled datasets, and supervised learning with full labels performance on the imbalanced classes. Table 3 result shows that SSL on raw data achieved the best performance. In Table 4, we know that the smartphone accelerometer gave the best performance comparing with smartwatch and gyroscope. In future research, we aim to extend SSL learning to other types of data beyond text or images, such as graphs, audio, and videos. Furthermore, it is anticipated that more advanced deep learning architectures, such as transformer, will be employed to perform self-supervised learning. Moreover, we hope to extend the current knowledge to other domains to tackle the domain shift problem in transfer learning. Thank you.